So our final topic of the course is the Fourier transform. This has nice parallels with the very first topic of our course, the Laplace transform. The Fourier transform is defined to take a function of t and turn it into a function of omega by calculating this integral. Maybe I should relate this to the Laplace transform to compare. So recall that the Laplace transform of your function is a similar integral. It's the integral from 0 to infinity of your function times e to the negative st dt. So the differences between the Fourier and the Laplace transforms are this factor of 1 over 2 pi. The Fourier transform's integral starts at negative infinity instead of 0. And instead of an s in the Laplace transform, the Fourier transform has a negative I omega. Let's do an example and then discuss why we're interested in the Fourier transform. So the Fourier transform of, let's say, the function f of t defined by 1 if t is in between negative pi and pi, and 0 if not. So the Fourier transform is a function of omega that is 1 over 2 pi, the integral. Now the integral in the definition goes from negative infinity to infinity, but for this specific example, the function f is 0 unless you're on the interval from negative pi to pi. So I'm going to integrate from negative pi to pi the function 1 times e to the negative I omega t. Now there are a couple of ways to do this integral. You could expand this using Euler's identity, or you could just integrate the exponential function directly. Why don't we do that? So this will be 1 over 2 pi times an extra negative I omega times e to the negative I omega t evaluated at t equals negative pi and pi. So you can plug in pi, you could subtract, you can plug in negative pi for t, and I think what you'll find is 1 over pi omega times e to the I omega t, I omega pi, so I'm plugging in t equals negative pi and pi. And if you do a little bit of the work and simplify a tad, I think you'll find this. So I decided to take the 2i and put it down here instead because I recognize that this is the sine function. I remember, for example, that sine of t can be expressed as e to the it minus e to the negative it over 2. So I recognize that's, or 2i, that's the form of the sine function. And so I think the final answer would be sine pi omega divided by pi omega. So there's an example of a calculation of finding a Fourier transform. Okay, so why is this an interesting integral? Well, recall the Fourier series of your function on the interval from negative L to L. So recall the Fourier series for your function f of t on the interval from negative L to L is given by f of t is the sum from negative n going from negative infinity to infinity of some constant Cn times e to the in times pi over lt. This is the complex form of the Fourier series. And the constants Cn when you write the Fourier series in this complex form, Cn is 1 over 2L times the integral from negative L to L of your function f of t times e to the negative in pi over L t. This was found by taking inner products and using the orthogonality of the sine and cosine functions, which of course are the real and imaginary components of this exponential function. This is motivation for the definition of the Fourier transform. You could see some similarities. In fact, you could make them look exactly the same. So if we take the L in this Fourier series to equal pi, and if the function f of t is 0 off of the interval from negative L to L, so like this previous function, maybe only between negative L and L, if L is pi, the function is non-zero, then the constant Cn is, well, I'm taking L to be pi, so it's 1 over 2 pi, the integral from negative pi to pi. I could write it as negative pi to pi, but you know what? I think I want to write it as negative infinity to infinity, because we're assuming that our function is 0 if you're not on the interval from negative pi to pi. So this could be negative pi to pi like our previous example, or I could just write negative infinity to make it match more exactly what the Fourier transform is, times the function f of t times e to the negative. Now if L is equal to pi, pi over L is equal to 1, and that term is not there anymore. And I find the Fourier transform evaluated at the integer n. So what this is saying is, under certain conditions, under the conditions when I take L to be pi and if the function is 0 off of the interval, then the Fourier transform gives you the coefficients in the Fourier series. The Fourier transform, however, is a continuous function of omega. It's a continuous function. So the picture might look something like this. So for each integer value, 0, 1, 2, 3, 4, even negative values, negative 1, negative 2, negative 3, negative 4. For each integer, I have a coefficient in the Fourier series. So maybe the coefficients look like this. The Fourier transform gives me a continuous function that passes through these values. So the Fourier transform might look something like this. Okay, that's just the beginning. The Fourier transform has many amazing properties, but this video defines the Fourier transform and hopefully motivates the connection with Fourier series. Okay, join us in the next video when we discuss the Fourier relations, a fundamental property of the Fourier transform. Follow me along there.